Here you can see the Andromeda galaxy as it appears across the electromagnetic spectrum. Select different wavelengths to reveal the story of how stars form and die in a galaxy that is very similar to our own. Andromeda is a large barred spiral galaxy. Seeing it in visible light, we're looking at the combined glow of more than 400 billion stars. That's around twice as many as our Milky Way. Yet, even in this limited wavelength range, we can learn a lot. We see dark band where dusty gas within Andromeda's spiral arms is blocking out starlight. And we see the blue glow of newborn stars. See, when new stars are born, some will be extremely massive, pumping out most of their light at blue or even ultraviolet wavelengths. But though they vastly outshine their more numerous lower mass yellow and red cousins, they die faster. The blue sheen of Andromeda's disk tells us that new stars have been born in this region within the past few million years. Any longer and the giant stars would already be dead. That's the case in the centre of the galaxy, where we see only the glow of much longer living yellow and red stars. This radio glow isn't from gas and it isn't from stars. We're looking at electromagnetic radiation from tiny subatomic particles, electrons, as they spiral in the vast magnetic fields that thread the galaxy. And those bubbles? Well, stars have strong magnetic fields, and when stars explode, those fields are blasted into vast bubbles. So you're looking at the fossils of past supernovae right there. They track the past history of star formation in Andromeda. In infrared, Andromeda looks very, very different. we aren't looking at stars anymore. Instead, we're looking at the vast tendrils of cool hydrogen gas that lives between the stars. It traces Andromeda's dense spiral arms. Each knot of gas is a giant cloud where thousands of new stars are currently forming. Our own sun formed in a place like this, in the Milky Way, not Andromeda, and it has since wandered very far from its birth location. However, the most massive stars never escape the clouds of their birth. Ultraviolet allows us to see the brightest stars in the galaxy. They are scattered through the spiral arms, tracing the regions of the most active star formation. We can't see them anywhere else because they explode as supernovae before leaving the spiral arms. But they don't just disappear without a trace. Supernovae leave their mark on the galaxy at radio wavelengths, and their corpses can be glimpsed in X-rays. See those pretty speckles? Some of those are shockwaves from past supernovae. Others mark the location of bizarre objects called X-ray binaries. These are powered by black holes and neutron stars, the stellar corpses left behind following the deaths of massive stars. If that star was originally part of a binary system, a system of two stars, then after its death, the black hole or neutron star may begin to cannibalize its remaining partner. The X-rays we see here are the final hiccups of gas from the remaining star as it pours onto the black hole or neutron star. Notice that the bulge of Andromeda is full of these X-ray sources. That tells us that there were indeed once giant blue stars there. Now all that remains are, well, their remains. Alpha Centauri is the nearest star system to our solar system. It's 4.4 light years away, so we see it as it was 4.4 years ago. Why? Because it takes 4.4 years for the light from Alpha Centauri to travel to Earth. This is Andromeda, our Milky Way's nearest neighbouring galaxy. We see it as it was 2.5 million years ago, when our pre-human ancestors were still in Africa. Imagine the scale of the universe when it takes light 2.5 million years to travel to our nearest galaxy neighbour. There are stars that appear young in the light that we see, but which by now have ended their lives in blazing supernovae. Light from this more distant galaxy has been travelling to us since dinosaurs walked the Earth 200 million years ago. However, 200 million years is an eye blink compared to the 13.7 billion years since the Big Bang. Notice that this galaxy isn't so different to the Milky Way or Andromeda. We're still looking at a very modern universe. As we look further back in time, we start to see a universe that is less and less familiar. We see this quasar as it was 5 billion years ago, when the largest black holes in the universe were feeding and growing like crazy, creating maelstroms of superheated matter. Yet, if we could somehow travel to its location right now, we would find a quiet galaxy with a giant black hole lying dormant in its centre. Despite what we detect through telescopes in the present, this quasar hasn't been active for billions of years. Even further back in time, we see that most galaxies are still in the process of forming. Small, primitive galaxies fell into each other's gravitational embrace and collided. This triggered storms of star formation that ripped across the new merging galaxy. The light from this starburst galaxy began its journey 8 billion years ago, when our own Milky Way was still forming in a similar way. And at the limit of modern telescopes, we see the light from the first galaxies to ever form. These islands of primeval stars formed from the raw hydrogen and helium gas produced in the Big Bang. Many of those stars were extremely massive and quickly exploded as supernovae. Those explosions enriched the early universe with the first heavy elements of the periodic table. Finally, we see the oldest light in the universe, the cosmic microwave background. This light was released only 400,000 years after the Big Bang, which happened 13.7 billion years ago. Back then, the universe had no stars, no galaxies. Instead, it was filled with a hot, dense plasma of hydrogen and helium. As the universe cooled, it suddenly became possible for the first atoms to form. As that happened, the universe suddenly became transparent, releasing its heat glow. We still see that glow today, shifted from hot infrared light to cold microwave as it travelled through the ever-expanding universe.